Hello, this is Stephen Neshiba, and I'm here to help you out with the computational exercise on visualizing thermodynamic surfaces. And so we'll just kind of take you through this a little bit. The top part of this is what we're calling self-assessments, and these are things that you're supposed to get out of this exercise. Of course, you'll want to read the introduction and look at the equations that are here. But what I really want to take you to is what to do in preparation for this activity. You'll have a computational notebook, set up a table of contents, and then on the starting page for this particular activity, write down equations 1 and 2. That equation 1 is for an ideal gas, and the second one is an equation of state for a van der Waals gas. You want to look up the units of energy, pressure, temperature, and volume in the liter atmosphere unit system, and the value of the gas constant in the liter atmosphere unit system. That's actually 0.082 liter atmospheres per mole Kelvin. And then you're going to look up some van der Waals parameters, A and B, for a gas of your choice. Let me just take you to the website, or a website where that will you can get that information. That's here. It's the second reference at this Wikipedia site. And if I just take you to this Wikipedia site, here we go. Then you'll just choose whichever gas you want from here. I think I've chosen, for this demo here, I've chosen krypton. So what's the next step? Well, I have some templates for some Python codes already, and they're on our week 1 website. And so first thing to do would be to download those script files. And what I'm going to do here is right click on that, and on ts1.py, and then I'm going to save it. Now I've already set aside a folder for these, and in fact I've already downloaded them, but here they are. And now then what we'll do is we'll go launch Canopy, and here's Canopy, and the first thing you want to do is open up this editor window. And we're not going to create a new file. You're just going to open up a new file, and that's what this. You can do this from the file menu, but I like to use this little icon here. And so it says, well, you wanna open up an existing file. I'm just going to go to where I put it all, and there we have ts1.py. And there we go. Now, according to your instructions here, I'll go back to the instructions for part 1. It says use Python to calculate the pressure of a gas. That's pretty straightforward. The temperature is 300, the volume is 25 liters. Let's see if that all came up properly. Let's see, the gas constant liter atmospheres, that looks good. The volume, that's 20 liters. I think I wanted 25. The temperature, that's at 298. I really wanted that at 300. Got 1 mole. Here's some van der Waals constants, but for the first part of this, I just need an ideal gas. Those don't even enter in there. I think I'm good to go. So when you're ready to run this script, you just press this green button up here, and if it says, oh, there are some unsaved changes, you just say that's fine. And there it ran. Now this reported here the pressure of the ideal gas. That was the result of this print statement right here, 0.984. So we're in pretty good shape. Now the second part of this first part of the exercise actually has us get the pressure not only of an ideal gas but of a van der Waals gas. That's right here, of a van der Waals gas. How do we do that? Well, that was equation 2 here. The pressure is equal to nRT and so forth. So I'm going to go back to Canopy and enter in some numbers here. Let's see, do I want a pressure of the ideal gas? No. I want the pressure of a van der Waals gas. Okay. Van der Waals gas. And how does this work? The pressure is nRT divided by, it's the volume minus this N times B. It goes in the denominator, and that whole thing is minus A times N squared. Now the squared in Python is a double star. and I'm going to divide that by the volume, which is also squared. Okay, now I don't want to just, this has already created the pressure variable for an ideal gas, so I think I'm going to give this a new name, van der Waals. Okay, and, oops, I forgot to put a 2 here. And not the pressure of an ideal gas. That's a van der Waals gas. Okay, and PVDW. Now, whenever you change a few things, even though you might not be done, it's good to kind of check them out. So I think I'm going to check this out. So I'm going to run it this way. Yeah, I do want to save it. Now, according to this, I've got the ideal gas has got this pressure. The van der Waals gas is looks like it's a little bit different. Fine. Okay. Then I think this is all looking pretty good. Now the last part of this exercise was to say go and get the percent error. That's the ideal minus the van der Waal divided by the van der Waal times 100. So let me go ahead and do that. Now you've probably already figured out that these little pound signs are just comments. So I'm just going to put in a comment here. Get the percent error. And I'm going to say error equals, let's see, I want the pressure of the ideal gas, which I've called just P here, and subtract away the pressure of the van der Waals gas, and I'm going to divide by the pressure of the van der Waals gas. Did I do that right? Not quite. And I get to multiply the whole thing by 100 because this is going to be a percent, and I just need to make sure I print it out. So I'm going to say print the error equals, and then you need to put a comma in between the things that you're going to print out. Error. Let's see if that works. And by pressing this button, and well, and I got an error here. It looks like it's about 0.2%. So that means that I've got the first part of this exercise done.